Hello everyone, can you hear me clearly? I'm not using headset. Okay, good. Yeah, thank you. So today we are continuing on the game theory basics. In the last lecture, we talked about the different concepts in game theory, and then also we explained some paradoxes, right? So one of them is this one, and which explains why surface routing will cause more severe issues when you have one free highway, right? So a free highway in the middle. Okay. Now, today we are talking about one remaining example in well, so actually it's a one remaining detailed example in the game theory framework. So this example is called isolation games. Now, what are isolation games? Well, so imagine that you have a number of players or owners of the shops. They want to open the shop in some area. And then when they open the shops, they would try to be far away from other shops. So the reason is, well, suppose the customers will go to the closest such shop to do shopping. And then if this shop is very close to another shop, then probably the customers, he can be allocated, or who will go to that shop will be less, right? Because some other people are competing with it. Therefore, those shop owners would like to locate their shops far away from each other. And then another scenario is the product design. So when you are designing a product, you would try to make your product different from other products, because this will, well, make your product more attractive, because, well, it has some kind of features other products do not share, do not have, right? And again, this has something to do with you want your own position to be far away from other people's position, right? Okay, so this is another example. And then actually in the literature, there is a very well-known game called Voronoi game. So let me explain Voronoi game first. So what is Voronoi game? So Voronoi game says everyone is controlling a point. Okay, everyone is controlling a point, and this point is on some kind of a 2D plane. And then these points together will divide the plane into several pieces, several regions. For example, if I have these 4 points, then the region probably would be divided this way. So I'm only roughly drawing the shape. Okay, so basically every point in the plane, they will go to the closest dot point, right? So we have 4 dot points, right? So these 4 points are the positions of those owners. And then every point on the plane, they will be classified or allocated to the dot point which is closest to it. For example, if you have a point here, and then this point is closest to this dot point, and therefore this point will be allocated to this dot point. Okay, and then you can use those lines, which is the perpendicular line cutting the middle of a line of a segment here, to divide the region into many different, many small regions. So in the end, you see this region will be allocated to this person, right? And this region will be allocated to this person. Okay, now of course this whole area has a boundary, right? Otherwise you cannot do much. Okay, you have a boundary. And then what is Voronoi game? So Voronoi game is doing the following. It says, okay, now every point you can move, all right? So every dot point you can move. If moving makes your area larger, then you will move. Okay, so basically everybody is selfish. It is trying to get as many area as possible, right, which are allocated to it. So therefore, now if we allow these dot points to move its position, and then for example, this one says, okay, if I move closer to the center, maybe I can get a larger area. Then I just move, right? So everybody would do the same. And therefore, in the end, if nobody is willing to move, right, then we say it's an equilibrium state, right? Okay, so this is a Voronoi game. Actually, it has some well, similarity to the isolation game we talk about here. Okay, Now, as we, there's one question. Okay, so Zia asks, before the start of game, Voronoi cell is already there. Yeah, so before the start of the game, everyone is on one position in the plane. And then, using these positions, we are able to generate the so-called Voronoi cell for each of them. Okay, so basically, we have a starting point. We have a starting position for everyone. And these starting positions will generate a composition of Voronoi cell. Okay, so Voronoi cell is just the area, right, which is closest to one point. So in this example, basically the area is something like this, right? We have 4 areas: the upper left, and this one, and this one, and this one, right? So we have 4 areas, each of them allocated to a unique dot point. So is it clear? Yeah, but remember, yeah, you're right. So if when they move, right, and the cells will change. For example, as I said, right, so if this dot point says, I move towards this direction, I move here, and then the cell changes, right, because now he will get more area, right? So if you use the line to cut, and then somehow he will get a larger region like this. Okay, he'll get a larger region. And therefore, okay, yeah, they can move to wherever they want. So when, for example, this point is moving, he can move anywhere, no limitation. All right. So as long as moving to that place will maximize the area he can get according to the division rule, then he will move there. Right. So remember that in the game theory basics, in the last lecture, we say that we have so-called best response and also sometimes better response. Right. So sometimes if you can improve your benefit a bit, then you will also do that, right? But if you have a very strong power of computation, then you may be able to compute the best response, right? Okay, so then there are 2 more questions. Do they move in a greedy way? Okay, so Wing-Chun, if you're greedy, just means that you go to the best position, then we can say so, right? So if you adopt the so-called best move, then, well, you can say they move in a greedy way. And then they do not move simultaneously. They move sequentially. For example, this one moves first, right? And then I ask this person, okay, would you move? And I say, okay, I will move. And then ask this one, right? So basically, it's a very good question, because in a better response or best response, we do need to differentiate whether people are moving at the same time or moving sequentially, right? So here you can just assume that they are moving sequentially. Okay, so any other questions? Okay, very good, very good point, okay? Well, in some of the cases, indeed, they will move along a cycle, okay? So they just never stop. That's very likely. Now, you will see it very soon. We are not talking about Voronoi game. Instead, we are talking about the isolation game. So the difference is now we are trying to maximize the distance from all the other players, right? Okay, so let me just show you some examples. Now here, this is one example, right? You have many players, right? Many players, and then these are possible points in the space. All right. So in isolation game, if you allow the players to move to any position, then it might be too difficult. Okay. So that's why we assume that they can only move to vertices or those brown points. Okay. They can only move to brown points. And then you see that at the very beginning, you have 7 players, right? 7 players, and the blue players are here, and then there's one yellow one, right? Okay, so there's one yellow player. Okay, and then here is the configuration, right? Now for the yellow player, we have a distance vector. All right, so this distance vector is d1, d2 until dk minus 1. Also here, you know that actually we have k players, right? We have k players. And then this distance vector is sorted. So d1 is smallest, dk minus 1 is largest. Okay, so here's the distance, right? So basically, if you focus on one player, this player has some distance to other players, and we sort those distances in increasing order, right? Okay, and then we have also a weight vector. So what's a weight vector? So weight vector is just how the yellow player thinks the distance method. All right. So one example. So for the W, right? So this W, right? This W can be 0, 1, 1, 1. So it can be any weight. Okay. So for example, if the first entry is 0, that means okay, this person does not care about the closest one. Okay, so we will have more examples in the next slide. Now, after you have this weight vector together with this distance vector, now we have a so-called utility function, right? So now each person's utility will be the distance multiplying the weight and then add them up. Now remember that when we multiply these two entries, we multiply in the order, right? In the same order. So basically this weight vector tells you, okay, how much I care about my closest neighbor. And this is W1, right? This is W1. And then W2 means how much I care about the second closest neighbor. All right, and so on. Okay, so basically so this is an input. This W1, W2, and WK minus 1 is given as input to the game. And then this distance vector is calculated, right, based on any location of those agents or players. And then based on these two, you are able to compute how much this agent get, right? How much utility this agent I will get. Okay? Well, so I guess I will, after showing you some examples, it will be even clearer. Okay? Now, let's see. About the W, right? About W. What can it be? Well, so it can be a single entry of 1. And then the other W is 0. So this one just means I only care about a neighbor which is ranked at a specific position in my distance vector. All right. Okay, so this is a single entry 1, right, for the weight vector. And you can also have some kind of monotonically increasing weight vector, monotonically decreasing weight vector. So increasing means that for the closer neighbor, I do not care them too much. But for the farther away neighbor, I care them a lot, right? Okay, and then there is also a game called all distance game. Actually, this one we already see it in the last lecture, right? So all distance game means the weight vector, every entry has a value of 1. Okay, so basically they are equally important to the player. I just add up all the distance together, and that's what I care about. All right. Okay, and then yeah, feel free to ask questions if you are not clear about the distance vector and weight vector. And now the game space. It can be, well, classified into asymmetric and symmetric. Right, we'll see an example of asymmetric game space very soon. And if it's symmetric, then there's continuous version and also discrete version. All right? And then for continuous version, well, the simplest one is 1D circle. All right? And then discrete version, well, there are many. For example, there's also 1D circle, and then hypercube, or maybe more general. Yeah, you're right. The game wants to get maximum utility. Or in other words, everyone tries to maximize his or her own utility. So this is the purpose of the game. All right. This is this is the how we argue for when certain player will move or not. Okay. Everyone tries to improve or increase his or her own utility. And then here, well, for the interest of time, we'll only talk about two. One is nearest neighbor isolation game. The other is total distance isolation game. So actually you can see that the total distance isolation game, we already have some knowledge earlier, right? So probably we'll only briefly mention this. Now we'll focus on the nearest neighbor isolation game. Okay. Now we come to the asymmetric space. So asymmetric means what? Asymmetric means for edge connecting two same nodes. If the direction is different, then the length is also different. So in this example, you see there are two kinds of edges. one kind is black edges. So there are black edges, and black edges has length 2. Okay, and then red edges, it's the other direction, right? So black is seems to be clockwise, right? And the red edges is anti-clockwise. And then red edges, they have length 3. Okay, so then let's see, there are 2 players, and they too are here at the beginning, right? Okay, and then this one will move. Oh, sorry, this is a mismatch. Okay, but well, you know the meaning, right? So the blue one will come to this node. Why? So the blue one, you see, the length to this. If blue one is here, and then he will look at the black edge, right? Because this is the distance he thinks the yellow one is from him, right? Okay, he thinks, okay, this is 2, right? This is 2. So it's better if I move here, because if I move to the right, then what I see will be this edge, right? Now I think, the yellow one has a distance 3 from me, right? That's better for me, right? So the blue one will move. Now after the blue one moves, then the yellow one says, okay, now I think the blue one has a distance 2 to me because I'm looking at the black edge here, right? I'm looking at this one. Okay, now I will also move. Well, I will also move. The yellow one will say, I move here. And then the blue one, to me, is the red edge, right? Because the arrow, right? So this is the blue one has a distance 3 to the yellow one. Now, you see, the whole thing is very symmetric. Well, the whole thing is kind of symmetric, right? So if after the yellow one moves, then this one move again. Because now yellow one moves, it makes the blue one think, you are closer. You move closer to me. Now I will move farther away from you, right? Oh, okay. So, volume is unstable. Let me see. Choose this one. Is this one better? I choose the same as system. So is it okay now? Okay, good. Yeah, thank you. Yeah, thank you for reminding me. So now so actually, I think that I should not talk that loud. That will trigger some unstable issues for the computer. So now you see in this asymmetric space, right? They will just move on forever, right? Because it's cyclic. You see that earlier, this one move here, and then the yellow one will move again, right? So basically, this will make the life of the game a disaster, right? And then actually, this example can be extended to n players, all right? So no matter how many players you have, as long as it is at least 2, right? And then you can construct a distance matrix like this. And then with this distance matrix, you will just cycle on forever. All right? So this seems no good. All right? Asymmetric space, nothing more can be done. And actually, they can prove that it is NP-hard to decide whether there is a Nash equilibrium. Oh, I see. Okay. Well, that's not very friendly. Well, so I guess for the time being, I can only continue, and well, I hope that this issue will be gone. Well, so is the current situation okay? Yeah, so I totally agree. A headphone will be nice, but it seems that I didn't have it here for now. Yeah, currently okay. Oh, Okay, thank you. So, yeah, do remind me if the situation becomes unstable. Okay, yeah, thank you, and thank you for your understanding. Okay, now we come to symmetric space. Now, if it's symmetric space, okay. So there's one question about NP hard. Okay. Now, the reason of this statement is the following. Now we have a game space, the many different instances, right? Many different instances. And then some instances have Nash equilibrium, and some does not. Okay? And then so now you see that in all this, the whole space, there are some good citizens and there are also some bad citizens. And the NP hard is saying that it is NP hard to decide for a certain candidate whether it is a good citizen or a bad citizen. Okay? So we know that they can. Sometimes they do not have Nash equilibrium, and sometimes they have. And then you give me an arbitrary instance. You ask me, oh, does this one have Nash equilibrium? Then the only thing I can say is, oh, I don't know. It is NP hard to decide. So did I answer your question? So if you want to decide whether there is a Nash equilibrium, you have to resort to exponential computing power. Polynomial time does not suffice. Oh, okay. Well, the first one means that we can construct examples. No matter how many players we have, they do not have Nash equilibrium, which means there are bad citizens which have 2 persons, 3 persons, and more persons. Okay. Yeah. Thank you for your question. Now, for finite space, both of them are so-called potential games. So I guess in the last lecture, we already talked about the potential games, right? So basically, it just means that after someone moves, then the game will, some metric of the game will increase. And then you keep moving, and then you keep increasing. So eventually, the moving process will stop. And then you arrive at the Nash equilibrium, right? So so for finite spaces, total distance game and nearest neighbor game, they are both potential games. And for hypercubes, well, there are some interesting results, but I will not go into detail because anyway, it's only an example. So for hypercube, if the weight vector is like this, which means I care about my closer neighbors, right? My closer neighbors. Then it is NP hard to decide whether some configuration has a Nash equilibrium, all right? Okay. Is a Nash equilibrium, okay? And then if the weight vector is this, I care about the farther neighbors, or including total distance. Then it is polynomial time decidable, okay? So give me a configuration. It's very easy to compute whether it is a Nash equilibrium or not. So this seems to be a very, well, contrasting situation, right, for the isolation game. Okay, so this finishes the last detailed or concrete example. The remaining part of this game theory basics, we're talking about some general knowledge about game theory. Now, so we know that game theory actually originates not from computer science. It's from somewhere like economics or other domains. But for computer science subjects, what we care about is what? One is modeling, and the other is the computational perspectives. For example, Nash, to say that there is always a mixed strategy Nash equilibrium, right, existing. And for computer scientists, they care about, oh, it exists. Then is it easy, or is it polynomial time computable, right? You give me an instance, is it easy to compute? But for economists in the old times, they do not care. They just say, okay, it always exists, right? How to find it? Oh, we don't care. As long as it can be found in finite time, that's okay, all right? But for computer science, for computer scientists, they care more about computational perspectives, how easy it is to compute the equilibrium, all right? Or how easy it is to decide a certain property. And then the with this marriage of the economics and computer science, we have a new area, and actually we already have some knowledge before, right? It's called computational games theory or algorithmic games theory. So these two will be similarly treated. Okay, so basically the main focus will be how to represent the games, how to compute and evaluate equilibrium concepts, and also the applications of game theory in certain domains. All right. Now, actually, I list well, some people here. They're very famous computer scientists who work on game theory. Okay. Now, well, I do not know all of them. Okay, so I only know 60% of the figures here. Now, oh, okay. So is it okay now? Okay, thank you. Now you can hear, right? Oh, good. Yeah, so next. So we talk about, we care about the computational questions, right? And then, well, if we say some computational questions, they're hard, then what can we do, right? Because usually we'll say, this problem is, or the equilibrium, whether it exists, it is going to be hard to compute. Well, then it seems that it's very bad news. And then how to bypass this kind of hard okay, so I guess let me so let me I don't know whether Zoom is adjusting my disabling noise cancel is too strong. Let me see. Audio setting, do you mean in the audio setting of Zoom? Audio setting of Zoom. Okay. Okay. Should be a checkbox of let me change to automatic, the background noise. I didn't take the automatic adjust microphone. So yeah, so I changed it to automatic denoising. Yeah, maybe. Anyway, let me rejoin. Well, I don't know whether I can rejoin or not. So current, is it still not okay? Now it's okay? Oh, okay, good. Yeah, I changed the denoising to automatic just now. So let me just continue for a moment to see whether there's still an issue. Okay? Yeah. Thank you. Yeah, and then when something becomes difficult, then we do have some way out, right? So one possibility is to study the games with special structure, right? Well, this is one way because, well, in general, it may be a general graph. And then if general graph is difficult, probably we can resort to the special graphs, right? Special graphs. And then, well, sometimes we may look at brute force algorithms to find equilibrium, all right? So, well, even though it's computationally hard, but, well, if you really want the equilibrium, then you still have some way out, right? You still have some brute force algorithms to compute. And then sometimes calculating the exact equilibrium may not be easy. So we may live with the approximate equilibrium, all right? So something which is close to the equilibrium status. And then if you relax it to this one, then probably we can have polynomial time algorithm, all right? That may be possible, okay? So what does it mean by approximate equilibrium? So do you have something in mind? So equilibrium says that you cannot, well, nobody can improve their his or her gain by moving or deviating, right? So what do you think will be a reasonable approximate equilibrium definition? Like approximation algorithms, right? But then oh, very good. Okay, so Jin says that at most improve by a certain percentage. Okay, well that's fine, right? Okay. Yeah. So Ziao, you are right, also right. So you will not move if moving will not bring you a profit higher than a threshold. So basically what you two suggest is one is multiplicative, right? So you do not exceed by a certain percentage. The other one is you do not exceed by an additive constant, right? So later on we'll see the difference of these two kinds of approximation. All right, and then well, sometimes you may also study alternative solution concepts. Okay, so that one will also be promising. So Wing Chun said to reach some percentage of true optimal. Well, this one probably well, because optimal is in terms of yeah. So I guess what you suggest is similar as Xuezhen, right? So basically, it's about cheating. Well, deviating will not get you too much more, right? In terms of percentage. So all these will be the possible relaxation of the equilibrium, right? Very good. Okay. And then, well, sometimes we may also have some kind of learning in games. All right. So, well, we know that nowadays learning is a very popular research field. All right. Everyone wants to have something to do with learning because that will be able to get into good venues of publication. All right. So, so just now, all the previous things, previous concepts we talked about, we are just computing one equilibrium strategy or an optimal strategy, right? Okay. But another one, we can learn how to play a game by playing it many times and updating your strategy based on your previous experience, right? Now, why do we do that? Well, actually, there are many reasons. One reason is probably the game's utilities they are unknown to you. Okay, so only if you have some setting and then you observe something and compute something, you know, oh, okay, this one means this much utility to me. All right, so sometimes the utilities need to be learned, and then well, sometimes it may be because some other players, they are not playing an equilibrium strategy. They are just playing in a very unpredicted way. Okay, so which makes your decision a bit harder because you know that earlier we assumed that everybody is rational, right? So they are reasonable. So when people are reasonable, you can compute your best strategy. But how about if people are not reasonable, are not rational? Then it may be difficult for you to compute the best strategy, right? Okay, and then sometimes it can be because the computation of an optimal strategy is hard. All right, so well, in that case, anyway, you are not able to compute the optimal one, then why not just learn from the previous experience, right? Okay, and then one last reason, it may not be a reason, it is saying that, well, actually our humans, we typically do learning, right? Okay, so just like, I believe you also have heard about the term called reinforcement learning, right? So that's also a kind of learning, and actually reinforcement learning, it has a very similar nature as dynamic programming, okay? It's just a dynamic version of dynamic programming, okay? So, so now by knowing the connections between these or among these concepts, you will have a better understanding of different terminologies, okay? Now this is about the learning, right? And then the learning strategies will basically correspond to the strategies for the repeated game. Because if you do not repeat the game, then there's no way you can learn, because after you learn, the game is over. Then it does not make much sense, right? So only if the games are repeated, then the learning will be meaningful, right? Okay, and then when so for the repeated game, so actually there is also a very famous term called no regret learning algorithms. Okay, no regret learning, it basically means that you do not regret, right? So it will compare to some optimal fixed strategy. All right, basically you are trying to change your decision every time, but what you compare with is the best offline strategy, which do not change at all. Because, for example, each person has 10 different choices, 10 different strategies, and then, well, you are comparing your dynamic adjustment of your strategy to the optimal strategy when you can only select one such strategy. Okay, so you cannot change. For example, I just fixed my strategy to be 1, or I just fixed my strategy to be 2. Which one is best? I don't know, because there are many future instances coming, right? So I don't know which fixed strategy is best. Then I will dynamically adjust my strategy so that the performance of my dynamic adjustment is not too bad compared to a fixed best strategy. Suppose you know all the future information. So this one has some connection to the online setting, right? Because in the online setting, we do not know future information. Therefore, you can only, well, based on your previous observation or strategies, you can compute the best, seemingly best one in the current slot, right? Okay, so there are also some other terminologies I will not go into. Not going to talk about in detail. Okay. Now, but one important thing is, well, if you do learning, then will it converge to equilibrium? Well, this one is more challenging, right? Proving something really converges to equilibrium, especially in the learning scenario, it will be very challenging. And again, this is only some kind of introductory things, so we will not go into detail about these specific topics. Okay. Now, about the computational questions in game, then what are the possible questions? Well, we have seen quite some of them before. For example, given a game, an equilibrium concept. Okay, so game and equilibrium concept. Does there exist an equilibrium, right? If there exists, then find one equilibrium or find all equilibrium. So all these are possible questions, right? And then also, people may ask, does there exist an equilibrium in which certain properties hold? For example, social welfare is at least K, okay, the total benefit of all the players, right? Or player I obtains an expected payoff at least V, okay? Or there's a unique equilibrium in G. Okay, so all these questions, they are reasonable computational questions one may ask when you are given a game and a corresponding equilibrium concept. So I'm just wondering, in the previous 5 minutes or so, is the volume okay? The mic? Ah. Oh, okay. Well, thank you. Yeah, sorry, really sorry that I forgot to bring the headset today. Yeah, but it's good to know that, well, you can still catch somehow. Yeah, okay. Okay, so now when you see your own problem, let me answer one question first. Since we concern social welfare payoff, etc., what's the meaning of calculating NE? What can we learn from? Oh, so yeah, we do care about social welfare or payoff, but Nash equilibrium is very important because in the reality, when people play in the game, you could imagine that they are trying to maximize their own benefit, because this is a trade-off between the socially optimal and the selfish outcome, right? So remember that in the last lecture, we talked about the price of anarchy, right? So when people play selfishly, they will arrive at a status where the social welfare may be very bad compared to the optimal social welfare. And we want to achieve the goal that this very bad, social welfare is not too bad, right? So we hope that the so-called POA is not too big, all right? So we try to see that under the selfish behavior of all the agents, to what extent the social welfare can be guaranteed. Okay, so this is the goal of making sure that social welfare is not too bad, given the selfish behavior of all the players. Okay, so did I answer your questions? Yeah. Okay, yeah, indeed. So basically, natural welfare is just trying to simulate the human behavior, and they will eventually arrive at some status, and then, well, after it is stable, you observe, right? So how good the overall configuration is, right? If it is very good, well, then we say, actually, this game design is not too bad, because even with the existence of selfish behavior, you can still achieve a relatively good social welfare, right? Okay, so now the next one is, I guess it will be more closer to your own domain. Now, basically, no matter whether you are a PhD or a master, so sometimes you may encounter some problems, right? So whether it comes from reality or come from coursework, etc., etc. Now, when you have a certain problem domain, and then you, for example, you already have a players, actions, or utilities, and then you will design the utility functions to be parameterized with parameters, and this will depend on agents' actions, right? And yeah, so Zio, I'll answer your question after I finish this slide. And then the second step is to identify a suitable equilibrium concept, and then look at the computational questions or evaluation questions, whether something is hard, right? Whether there are some algorithms computing some good solution, etc., etc. Right? And then this third step, you may conduct simulations to highlight the equilibrium behaviors using real-world parameters or instances. All right. So basically, simulations sometimes will be important because, well, some questions or some problems you may not be able to compute mathematically all the equilibriums, but by experiments you are able to observe, well, actually this type of things may happen in reality. It's a kind of equilibrium status, and it may happen, right? Because it may happen, then it may give us some insight about, well, when we tell the people how the games look like, and then we could give them some hint, right? So for example, you can adopt this, that, and then, well, everybody will be happy, right? At the same time, the social benefit will not be hurt too much, right? Okay. And Zio is asking, sometimes designing the algorithms to compute NE is to guess how will these rational, yeah, you're exactly. So basically, this comes to well, so no matter whether you design algorithms or you do run simulations, you are trying to see how the rational agents will act. Yes, you are right. Okay, so basically, game theory, it has two sides, all right? One is theoretical side. You are trying to use the algorithms, right, to compute something, all right? And then when you have that results, you may tell people, okay, here are the possible outcomes. Then you may negotiate which outcome you will arrive at, right? You would like to see in the future, in the end. And then another thing is by experiments, right? Running experiments will also give you some insight about how a stable status in the game will look like. Okay, yeah. So for these, I guess they are closer to many of your own research domain or study focus. Okay, now one thing which is very interesting is called security games. Well, this is the game I heard about maybe 5 years ago, but they are really very, very useful and also interesting. So what are security games? Well, so security games basically it's about well, there are two roles: attacker and defender. All right, but the attacker and defender they will be put in a different scenario in different security games. For example, they so one example is Coast Guard. Okay, so Coast Guard means what? Okay, so you have some patrols, right? And then there are some people who is who is illegally penetrating or entering the boundary of a country or a city, and then because you have a limited manpower or resources, you cannot put your patrol resources everywhere, right? So it's not possible. You can only do, okay, I put some resource here on one Monday, and put some resource there on Tuesday. And then the attacker, which is the illegal immigrant or some other people, they may observe your strategy and they try to use their best strategy to increase their chance of escaping your vigilance, right? So basically, there is just like a defender and a attacker. They're doing it. They're playing a so-called game, right? And everyone's defender is trying to maximize the security level, right? And while the attacker is trying to infiltrate, right? So or try to find the loopholes of those patrol so that they can enter, right? Okay. And then there's also another category of security games called green security games, which is also very useful, like wildlife, right? For example, tiger or elephant, and then some illegal persons, they would like to hunt for tiger and the elephant, now which is actually not good. And then, you need some resources to be deployed to the forest, to those regions, to prevent those kind of illegal hunting, right? And then again, you need to, care about whether or where and how much resource you put, so that you increase the overall defending result, right? So they will not, so that the bad persons will not gain too much, right? Okay. Now, and also there are some other categories of the security game, like opportunistic crime games or cybersecurity games, etc., etc. So if you are interested, you may go to the internet to find those papers on these types of games. Okay, so this is about the real-world security games, which are very interesting. And actually, if we have time, I'm also going to talk about one special kind of we cannot call it security game. It's kind of defender and also network defending game. It uses the basic algorithms in a very, very elegant way. Okay, so if we have time, I'm going to spend 1 hour on that too. Okay. Now, so other than the security games, then we also have some other games like the influence games. Actually, I can talk about influence maximization games. So this one happens on a network. Okay, so you have a social network like this, and influence maximization will talk about the following. So suppose the Apple, okay, so they have some new products, and then they will select some people to give free new products. Okay, for example, right? There's a red person here, right? So it's okay. I give you an iPhone for free. Okay, and this person probably will advocate the Apple product to his neighbors, right? Now, if this is a very big star, all right, maybe what he said will be very, very useful or very influential. People hearing what he says or what she says will be greatly affected. So, for example, she said, "Okay, this iPhone 12 is very good," and then, maybe all the people who are affected by him or her, they will buy the new iPhone, and then by doing this, the Apple will earn a lot of money, right? So basically, it's about giving certain number of people a free sample of a product, and then let these people advocate your product for you, and then these people will tell its neighbors, and the neighbor will tell their neighbors, etc., etc. And then there are different propagation model which can characterize the behavior of how those information will propagate in the network. And then the goal of the game is to select, for example, if you only have 10 iPhones to give out, all right? So then you need to decide which 10 people you give the iPhones for free, so that in the end, the number of people who will buy iPhones is the largest possible. Okay, so that seems to be a very, very realistic and also useful model. All right. And then, well, of course, there are many others, but I'm not going to talk about details about these games. If you are interested, well, you feel free to search online because, well, actually, we cannot exhaust all the possible games. I can only pick some representative games to introduce to you. Okay, so yeah, and then just to summarize a bit, right? So basically, for all these games, right? So these games, they are games people experienced in their own domain or research field. And then by proposing those games, they have three contributions. One, they introduce the game theoretic models for their domains, right? As I said before, if you have your own domain of games, and then you can model the game. And then second, you will try to analyze and compute Nash equilibria, right? Or other solution concepts. And then in the end, of course, it's optional. You can run experimental evaluations of your algorithms, right? So this is also a kind of the research flow you will experience for certain problems in your own domain. Yeah, you're right. So Wing said it seems that there are many parameters to consider and some are hard to quantify. You're totally right. So modeling is also one very important thing in the game theory study because, well, of course you can study existing games, but for existing games, usually people already have a good understanding of them. So more importantly, it will be more useful to consider some games which arise in your own domain, and then you try to model it, which seems to be, well, quite different from the existing games. And then you can go ahead to study the solution concepts of that game. So actually, the 1 hour session I mentioned earlier has this kind of flavor. Now, because that is a game where which we come into that come into my mind about 2 years ago, and then well, at that time it seems that motivation-wise it's not that persuasive, but eventually we make that persuasive, and then we also have very elegant results for that game. Now, I mean, well, not complicated solution. Just well, the solutions are not complicated. They're easy to understand, but well, they're solving an interesting new game. Okay. All right. Okay. So here are the slides some of the slides I borrowed. So basically, you know that the beginning part of the course about those classifications, it's from this site. And then the last several slides about the general framework of the game comes from Hao Chen, one tutorial by him. And then the middle one, well, most of them I made it by myself. Okay, so I guess we'll take a 5 minutes break and feel free to ask me questions. And then we will cover the remaining part of the randomized algorithms slide. Okay, so Sina is asking the time of midterm exam. The midterm exam is week. I need to double check. I remember it's week 10. And then if it's week 10, that means it should be the current week 11. Well, let me just check the. Oh, it's not March the 17th. Earliest date is March the 24th, I think. Today is March the March the 3rd, right? And then next week, March the 10th, we will complete the cooperative game topic. And then March the 17th, we will have a guest lecture from Japan. He will talk about certain application of game theory, which he is expert on, and also it will be good to have some expert talking about this one aspect of game theory. So basically, the earliest time of midterm is March the 24th. Yeah, we can do March the 24th. Let me just double check the canvas. Yeah. So according to original schedule, it's March the 24th, which is week 10. Now, because we postponed one lecture, we may also do it in week 11. So up to you. I guess between March 24th and March 31st, I guess I will do a polling. Okay. So yeah, because I guess that we will possibly cover one more application of game theory before the midterm. That may be better slightly, but well, it's optional. It's also okay to just give the midterm after the guest lecturer. Now, because so basically the materials in guest lecture I will not. I need to think about whether we would include certain questions. Probably will. So I believe the guest lecturer will also contribute one question to the midterm. So I will do a poll. If you would like to stick to the original week 10, which is March the 24th, then choose yes. If you want to do it 1 week later, March 31st, you choose no. Okay, so I will see your preference, whether it's March 24. 24 is yes, and then 31st is no. Okay, so just want to let you know that every count matters, every vote matters, because sometimes the count will be very close. So try to express your opinion. Okay, so how much more will be included if 1 week later? So if 1 week later, we will include one more lecture's material. Okay, so that's the difference. So if you think more game theory is better, then maybe, well, 1 week later will be better. Yeah, but anyway, we will follow the majority of the votes. I will put the vote here. In case somebody come back, you can still tick. Remember, yes means March the 24th, and no means March the 31st. Okay. Oh, you mean, yeah, OJ deadline, yes. OJ deadline, we could change it to week 9, for sure. Yeah, because we postponed one lesson. Okay. Yeah, and then I see Yuchi said the week 11 is close to many deadlines from other courses. Okay, then maybe week 10 is a wiser choice. And actually, yeah, let me just wait for a few more votes. Although now the decision or the result is already somehow unchangeable, because one option is about to reach majority. But anyway, let me just put it here, and then we will continue the algorithm one. So you can see in my sharing about counting distinct element. Is it right? Can you see that? Okay, good. All right. Now, this is just a review. All right. So remember that in the randomized algorithm lecture, we talk about the streaming algorithm, right? So streaming algorithm means the items come one by one, and you need to decide whether you keep it or do some operation or what, right? So basically, you have a very limited storage. You cannot store every item coming in. All right. So then, what do you do in order to make your future answers to certain queries accurate as possible? Okay. So now let me just continue by giving this following example. So counting distinct elements means that you have a bunch of items coming in. I want to know how many distinct elements you have. All right. For example, you have 1, 1, 2, 2, 3, 3, altogether 6 numbers. Then the distinct elements will be 3, right? Because only 1, 2, 3 they are different. All the others they are the same as 1, 2, 3, right? Okay. And then we want to estimate the number of distinct elements up to a certain error epsilon with a probability 1 minus p. Okay, so we hope that with a high probability we are able to answer the question, okay, within a certain error epsilon. So this is a bit a bit challenging. So sometimes we go for the simpler goal. The simpler goal is, if I give you a t, you need to design an algorithm which with probability 1 minus p will answer yes if your actual distinct number is larger than 1 plus epsilon times t. And then you answer no if the distinct numbers are less than 1 minus epsilon t. So basically, imagine if t is 100. If t is 100, epsilon is 0.1. Okay? So if this is the setting, then what does it mean? It means that if the number of distinct elements is larger than 110, I will definitely answer yes. And if your number of distinct elements is less than 90, then I answer no. Okay? Now you may ask, how about if my distinct number is between 90 and 110? Well, I don't care. All right? If your distinct numbers is well in the middle range, I don't care what answer you give me. You give me yes or give me no, I just don't care. I think, well, I will not request you to do very accurately for that range, the ambiguous range, right? But for the extreme range, I need you to be accurate. Okay, so is it clear? So basically, now we only talk about the simpler goal, okay? The simpler goal, I give you a target number, all right? How many distinct elements I'm looking for, all right? And then if the real number of distinct elements is larger than a certain fraction of the given number, then you should answer yes, because I'm expecting that, right? So I'm expecting you to tell me, okay, there are indeed a lot of distinct numbers in the stream, right? Now, otherwise, if the distinct number is very small, then you should tell me no, all right? And then if you have this simpler algorithm, then you can run the algorithm for many rounds using values 1, 1 plus epsilon, and then etc., etc., okay? So that, well, in this way, you are able to do some kind of accurate analysis. So Ziao is asking, is P a given parameter? So P is actually, P, you can decide it, okay? As long as your probability, for example, your probability is not too small, okay? For example, with probability 0.6, I can output the correct answer, then it's already good enough, for example, okay? Later on, we'll talk about how to make it bigger, all right? So this P is your algorithm's output, not the given parameter, okay? Your algorithm decide what P is. Okay, good. Now, here we talk about a very simple algorithm, all right? What is that? Now, I hope that you still remember what bucket sort is. So anyone who, well, is it okay? So did you learn bucket sort before in your undergrad study? Well, let me use the questionnaire. Okay, so the questionnaire, I'm closing it. Actually, it's already not big change. So although the yes answer didn't take the majority yet, but I believe that it's already slightly majority. Okay, so basically we will still use the week 10 option. All right, March 24th to do the midterm. Okay, and then I will use this questionnaire to ask about bucket sort. Okay, so bucket sort, did you learn it before? Yes or no? Okay, so it seems that 50-50, oh, no dominates. Well, that although it's quite unexpected, but I guess I would need to tell you about bucket sort. Okay, thank you. Okay, so bucket sort means the following. I'll use one example. So I have, so suppose I'm sorting 9 digits, okay, nine numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay. So suppose the numbers I have is 4, 6, 8, 9, okay. And then bucket sort is very easy. Bucket sort says, okay, 4, you go to bucket 4. So you see here I draw 10 buckets, right? These 10 buckets can correspond to 0, 1, 2, etc. until 9. And then 4 comes in, I put it here. 6 comes in, I put it in the 6th bucket. And then 8, I put it here. And 9, I put it here. And then I output all the numbers from left to right. It becomes 4, 6, 8, 9. Done. Okay, now, of course, this is only a simple version of bucket sort. All right, now, actually, the numbers that come in can repeat, right? So you can have many 4s. Okay, you can have many 8. So when this comes, then this happens, whenever you see a 4, you put it in bucket 4. All right, so eventually, bucket 4 will have many numbers, right? 4, 4, 4, many 4s. And then 8 will also have many 8. But when you output the whole order of the sequence, you still follow 4, 4, 4 something, and then 6, and then 8, 8, 8 something, and 9. So this is what you do for bucket sort. But I guess I will not go into detail about how bucket sort actually is used to do the so-called radius sort, which is more useful. All right. But that's another story. All right. So they belong to the data structure course or data structure and algorithm course earlier. So I will not repeat. For now, it's sufficient just to know that bucket sort means I see a number. This number is 4. I put it in bucket 4. This number is 6. I put it in bucket 6. That's it. Okay. Well, now, why do I raise this issue? So because the algorithm I'm going to introduce is very similar as this bucket sort. Okay. So let me just do one thing. Okay. Yeah. So the algorithm goes like this. We choose a random set of coordinates. Okay. Now, remember, in the previous page, we say the streaming elements is coming from, so the range is 1 to m. Okay. So all the possible values, they are either 1 or 2 or 3 or up to n. Okay. So these are all the possible values. So now I choose a random set of coordinates, which means from 1 to m, I choose a random set to store. Okay. And then I maintain a sum of x over this random set of coordinates. Okay, so one example. Suppose you have 100 possible numbers, 1 to 100, and then I chose 4, 10, 16. I only choose 3 of them. Okay, randomly choose. Okay, and then I say, well, if your numbers are 5 or 6, I don't care. I do not store you. If your numbers are 4, okay, I put one number here in bucket 4, right? In 4. And then if your number is so radix sort is a combination of bucket sort in different rounds. But I will not go into detail. Yeah, and you are right. It's similar as radix sort. So now the algorithm will do the following. It says, since my current focus is only 4, 10, 16, now let me see whether I ever see any such number coming in. If there is any such number coming in, I'll put yes. If none of them ever comes, I'll put no. Okay? So this algorithm is super easy, right? You say, I pick a random set, and then I just try to observe whether I have numbers in this range coming in, right? If yes, I say, then my answer to your question is just yes. If no one comes, then my answer to your question is no. Now, let's see the probability that the sum is 0. What's the probability? Well, actually, it's easy to compute. So this is 0. It means that none of the numbers, right? None of the numbers are 1, right? So I choose some index where nobody come, right? Okay, so the distinct elements, suppose there are 6 distinct elements, okay? 6 distinct elements. Then every such element has a chance 1 minus 1 over t not to be chosen, right? With 1 over t chance, this index will be chosen, right? You see, with 1 over t probability, I will choose this index. Then with 1 minus 1 over t probability, I will not choose it. So if for the 6 distinct elements, none of them is chosen, then my sum will be 0, right? Okay, so the probability is 1 minus 1 over t to the power of the number of distinct elements. Okay, so that's the so-called probability, right? If you have 6 elements, then I have such probability that I didn't manage to find the answer, your correct answer. Well, so here I'm skipping something. So this is, here I'm just showing you how to compute the probability, but I'm not showing you the detailed steps about the argument. So also, I'm not going to require you on that. Just have a rough flavor of it will be sufficient. Okay, so now let's come to the next part about boosting probability. Earlier, Ziao asks about whether P is a given parameter. My answer is no, right? So your algorithm decides it. Now suppose now we already have an algorithm where if the distinct elements is larger than this, with probability less than this, I will output the answer, correct answer, okay? And then when this is smaller than a certain threshold, then with a larger probability, I will output a good answer, okay? Now, but these probabilities actually seem not too good. For example, we would like to see a probability of 80%, 90% outputting the correct answer, right, in the right domain. But actually, at the first time you design the algorithm, basically the probability will be very close to half. Okay, so for example, I said I have a probability 0.51. Okay, I give you a right answer. Then you say, that's useless, right? 0.51, it's just very similar as random give me answer, right? Give me one answer. But remember, this is not useless. The reason is we can boost the success probability. How? For example, in our case, just now we say we select one subset. Now, in order to boost probability, we can select a number of sets. So just now we select 4, 5, 4, 6, 16, for example, and then you may also choose randomly 5, 9, 12. Okay, so you randomly choose a multiple sets S, and then if every one of them tells you, oh, I'm 0, then you output 0. As long as one of them tell you, I'm not 0, I output not 0. I can output yes, right? So you see that only if all the subsets tell you 0, then you output no, right? As long as one of them is not, then I give you yes. Then using the so-called Chernoff bound, you can boost your success probability to a value very close to 1. Okay? But again, as I said, this is not a focus of this course because it belongs to probability theory. But I'm just trying to show you that by using this kind of approach, you are able to boost your success probability of an algorithm which seems to be not so good. All right? Okay, so is the current, so basically this is the end of the streaming algorithm. Oh, sorry, DE, right? So what is DE? DE just means disjoint element, okay? Remember, disjoint element means DE. number of disjoint element, number of different numbers. Okay? Is it clear? How many? Yeah, okay, good. All right, so now we move on to the amortized analysis. So amortized analysis, it's very similar as average case analysis. I believe that in your data structure course in your undergrad study, you learned average case analysis, although we rarely use it, right? So amortized is similar as average, but different. Okay, so now let's just try to know what amortized analysis is. Now this basically has something to do with a sequence of operations. For example, in a binary tree, you do a lot of insertions and deletions, and then each insertion, deletion, they may take different amount of time. But if you add all of them together, take an average, then probably the average insertion time is not that bad. Okay, so there may be one insertion which takes a lot of time, but if you average it over all the operations, that may not be bad. Okay, so this is the basic philosophy of amortized analysis. Now the reason I say it's different from average case analysis is that average case means what? Means that, for example, if you do sorting, right? Yeah, 1, 2, 3. If I give you a sequence already increasing, then certain sorting algorithm will give you a very quick running time, right? Basically, nothing need to be done, right? It's already sorted. So some sorting algorithm will return you the answer very quickly. But if my sequence is 5, 6, 5, 4, 3, 2, 1, that same sorting algorithm may take a lot of time. Okay, so average case analysis says, you give me an input, I have a running time. You give me another input, I have another running time. So I will add up all these running time for all the possible inputs and then make an average. That's the average case analysis. How about amortized? Amortized says, okay, your input is fixed. Okay, your input is just a one insertion, one deletion, one insertion, etc., etc. Okay, the input is already fixed. Then some operation may take a lot of time. For example, this deletion takes a lot of time. This insertion takes a lot of time. But no worry. If I add up the operation time over this timeline, and then the total operation time, total running time is not too big. Okay, so this is amortized analysis. Okay, well, just want to get a rough feeling about whether you know the difference between average case analysis and amortized analysis. Yes or no? Well, it seems that it's half-half. Okay, well, anyway, again, that's not a major focus, all right? I'm just trying to show you the amortized analysis, how to do it. Okay, now, basically, we have well, different approaches. One is probabilistic analysis, all right? And then, oh, sorry, my bad. Okay, so amortized analysis here, we say that there is no involvement of probability. So there's no probability, okay? And then, as we said, it's the average performance of a sequence of operations. Even though some parts, right, this part may be very expensive, but it's okay. If you do an average over all the operations, then it's not that expensive. Okay? And then, so actually here, right, the probabilistic analysis is exactly the average case running time we are talking about just now. Okay? So this is taking an average over all the possible inputs. Okay? All the possible inputs like this, right? All the possible inputs, not a operation. All right, and then actually, well, you may also say, if we talk about operation, you may also do similar things. But then for average case analysis, you need to consider all the permutations. For example, insertion, deletion, insertion, insertion. And then you may swap it. Okay, how about deletion first, and then insertion, and then deletion, another deletion, right? And so on, so on. If I permute it, okay, so average case analysis says, among all the possible permutation, all right, every one of them I calculate a time. And then I do an average. That's the average case running time, right? And amortized says, I fix your sequence, all right? And then I only care about the total of these operations. And some of them are expensive, some of them are, well, cheap. All right, so add them up together. On average, it's good. Okay, and then I see another question. What does operation mean? What's the difference between input and operation? Oh, okay. Actually, this is a very good question. Now, actually, this kind of input, you can also consider it as operation. Why? You can consider it to be, I give you a 1, I give you a 2, I give you a 3, right? So these are also operations. Although for sorting, you know, I have an array, which is 1, 2, 3, 4, 5, 6, and then do something, right? I do something. But you can also consider it, if your algorithm can only look from left to right, you can consider it to be left, well, I see 1, and then I see 2, I see 3, I see 4. Okay, now this one will be more clear if you consider the so-called insertion sort, right? Because insertion sort, every time you check a new number and put it in the right place in the old numbers, right? So in insertion sort, this sequence of numbers, they are just like, you give me a number, right? Give me 1, right? And then give me 2, give me 3. You can consider them equivalent to operations. But for some algorithms, if they look at the whole thing, right? And then, well, it may not be difficult to interpret as operations. So operations, what are operations? You will see very soon, because for amortized analysis, it can only be used in analyzing operations. So I understand that some of you didn't choose a no just now because, well, you didn't see a real example. So maybe after you see the example, you will have a better feeling. Okay. Now for amortized analysis, we have 3 kinds of ways to analyze, but they most of them, they are very well. So 3, right? So these 3, they are using different approach, but in a high level or in the principle will be the similar. Okay, so we will talk about aggregate analysis, accounting method, and also potential method. Yes, Wing-Chun, you are right. Okay, so let's look at an example. So the first example, now here we need to know some data structure, right? So that's why I assume you all know data structure because well, our admission criteria has data structure. Well, I cannot guarantee that, but okay. So we all know stack, right? Okay, so this stack operation, we have push and a pop, and then well, push means I put one. Now I draw a stack. Okay, push means I put one item in, right? And then I push another one. And then I may pop, right? I can get rid of this 2, and then get rid of this 1. Okay. Now, if you only have push and pop, you don't need to do amortized analysis because push and pop, both of them only takes one time, one step, right? But now, suppose we allow multi-pop, which means if you have 3 items, I can pop all 3 out. This is considered as one operation. Okay, so this is multi-pop. Okay, yeah. So basically here you see that the code. So as long as it is not empty, right, and k larger than 0, you pop, right? So basically, I would like to pop k elements from the stack, right? But you see, well, if in one operation you pop k elements, that operation will be very expensive. Right? You need k times. That's not good, right? Okay, so now we want to analyze the amortized running time of n operations. Push, pop, and multi-pop. Okay? Now you know that multi-pop, in the worst case, will take you on time, right? Because I can do multi-pop as n, right? I can pop n elements. That's not good, right? The single operation takes on time. Therefore, if you use the traditional worst case analysis, you may say, then in the worst case, all of them are multi-pop, and then each of them take on time. So altogether, it will be on squared, right? On times n multi-pops, right? Okay, well, but on squared seems very pessimistic. It's not tight. So let's do an analysis. So we are doing the so-called aggregate analysis first. So what are we doing? Now, actually see a sequence of n operations on an initially empty stack cost only O n, which means if we do amortized analysis, if you have n operations, no matter how you push and pop, right? You put something in, you pop something out, and so on and so on. You do altogether n operations. Actually, the running time is O(n). It's not O(n) squared. Okay, so let's see. Now the reason is what? The reason is each object or each number can only be popped once. Okay, even if you do multi-pop, all right? Now, suppose this 3, right? CC is 3. The 3 is pushed into the stack, and then say I do multi-pop. Then 3 is gone, right? Will he enter again? Will this 3 enter again? Enter the stack again? If, well, suppose you only, well, every number you can only deal with it once, okay? So this same 3, they will never enter again, right? Okay, so if this is the case, you see, every number, right, it can only be popped once. So, number of pops is at most the number of push, right? How many push? And then I can at most pop so many times. Okay? And therefore, how about the average cost? The average cost is O(n) over n, which is O(1). Okay? Yeah, so the main reason is if you do n operations, you at most put n numbers in, and each number can only be popped once, right? So altogether, you may only have about 2n or something like that operations, or the time needed will be about 2n at most, right? So basically, it will be O(n) over n, and the amortized running time for individual operation is just O(1). Okay. Now, the amortized cost in the aggregate analysis will be defined as the average cost. Okay, so this is the analysis for the push pop. Okay, on average, right? On average, how many operations you will need to pay if you do n operations, right? So we calculate the total, right? We calculate the total needed cost and divide by the total number of operations, right? Okay. Now, actually, there is another example which is also very interesting. So this example is called binary counter. Okay, counter. Well, when you learn some undergrad course in digital circuit, I believe that you have done experiments of counter, right? Digital counter. So counter is what? Well, counter is just I have k digits, right? Each digit is 0 or 1. So at the very beginning, they are all zeros. Okay, and then say after one time step, I will flip this 0 to 1. Okay, that becomes 0, 0, 0, 0, 0, 1. And then the next moment, it becomes what? It becomes 0, 0, 0, 0, 1, 0, right? It becomes 2, the binary 2. So basically, it's doing binary count, right? The counter in the binary number. So from 0 to 1 to 2 to 3, so basically, you just advance, right, into larger and larger numbers. Okay, so here is a code, right? So we how to increase a, how to increment a. Well, firstly, we let this I be equal to 0. As long as I is less than k, which is the whole length, right? And then also ai equals 1, we flip ai. So that means when you see something like this, right? If I want to increase this number, how to increase? Easy, right? When I see a 1, I change it to 0. When I see a 1, I change it to 0. I see another 1, I change it to 0. Now this is not 1. Okay, then I change this 0 to 1. Right? So 1, 1, 1 becomes 1, 0, 0, 0. Right? So whenever I see 1, I change to 0 and increase the index. Right? So if eventually your index is still within the range, I change you to 1. Okay? So this is a counter, right? This is a binary counter. Now the question I ask is, how many times you flip the point, flip the digits? Because You see, in the counter problem, there may be one operation which need to flip a lot of digits or bits, right? For example, if your number is that something like this, 0, 1, 1, 1, 1, 1, 1, 1, okay? And then you increase this value, it will become 1, 0, 0, 0, 0, 0, 0, 0. So you flip all the bits, right? That's very bad. In that single round, you flipped k bits. That's bad. But that's not too bad. Well, so you see, if you use the traditional worst case analysis, you see, I would need to flip k bits in the worst case, and then a sequence of n execution will take onk in the worst case, right? Okay, but this bound is not good. The type bound is on, nothing to do with k. Then you may wonder, oh, why? Why on? K is not playing a role. Well, so actually, if you do an overall analysis, you will see the reason behind. Okay, so you see that this is a whole flipping story. You can see the last bit is flipped every time, right? Whenever you increase by 1, you change from 0 to 1 or change from 1 to 0. Okay, no escape, right? Every operation will flip it, right? So it flipped n times. And then the second last digit, which is A1. This one, it will be flipped every 2 times, right? It will be stable for 1 round and then switch to 1. And then keep stable for 1 round and switch to 0. So basically, A1 will only be flipped n over 2 times, right? Okay, then how about A2? Similar. You see, when you look at A2, it will stay stable for 4 rounds, right? You see, 4 rounds. Okay, so it will only be flipped n over 4 times. And then every AI will be flipped n over 2 to the I times. And total number of flips, you add up all these numbers together. So I believe by now you are very familiar with how to add n over 2, n over 4, n over 8, right? They are just 2n. Okay, so in other words, the total number of flips is 2n, and then you divide by the total number of increase function, right? You increase for n times, so 2n over n. On average, it's only 2 flips every time, right? Okay, so aggregate analysis just tells you, how about I compute the total number of actions you take, okay? And then divide by the total number of operations, and I'll have an average, right? Okay, so this is the second example about binary counter. So you see that for binary counter, this amortized cost per operation is only 0.1, right? Only 2 steps. Okay. Now, up to now, let me just do another polling. Okay, so up to now, do you have a better understanding about amortized analysis? Yes or no? So I mean, better understanding. Good. Now I see a dominating number have a better understanding. Still some didn't. Well, don't worry. We have a second method to introduce. Okay, so let's continue. Now, the accounting method may be easier to understand. So what does it mean? Well, accounting method means I allow you to deposit some money or use some money and so on. Okay, so we will charge. We will assign different charges to different operations. So the amount of charge is called amortized cost. So amortized cost is roughly actual cost, but only roughly. Okay, and then when the amortized cost is larger than the actual cost, we will save the difference in specific objects as credits. So basically, if you, so later on we'll see examples, okay? And then these credits can be used by later operations whose amortized cost is less than actual cost. Okay? Now, remember that in aggregate analysis, we do an overall computation and divide by the number of operations, right? So here it's a bit different. It's more fine-grained. So let's see. Okay, now there are some conditions here, but I guess I will not repeat it. Well, I guess using examples would be easier. So let's see the stack example. Okay. So the stack example, you know, we have actual cost of push, pop, and multi-pop. All right. So push takes one step, right? Push one number in. Pop takes one step. Multi-pop takes so many steps. What's this? Well, usually it's k steps, right? Because you pop k elements, you need to pop k elements, right? So the cost is k. So this is the actual cost. Now we assign the following amortized cost to these operations. For push, we assign 2. For pop, we assign 0. For multi-pop, we also assign 0. Okay, so what does it mean actually? So you can imagine the following. When you push a number, you will give him $2. Why? Say, okay, for $1 is for pushing it in, right? I know in the future it might be popped. So why not I just give you $2 at the very beginning? So when you push a number in the stack, I just directly give you $2. $1 for this push, and another dollar for the future pop. So basically, in the future, when you pop something, I do not need to pay you anything because I already prepaid that, right? When you push one item in, I pay $2 as a cost, okay? So just once more, $1 for your current push, the other dollar for the future pop. Although I do not know when in the future you will be popped, I don't care. Now, it's up to you, right? So in sometime in the future, you will be popped. At that time, please take that $1 away. Okay? So that's the major principle. All right? So if you do this, you see that it's just like when you push, I deposit $2 in the bank. And $1 you already take away for this push, right? But there is another dollar remaining in the bank. And then for the second push, I again deposit $2 in the bank. And $1 you take away because of the push, and another dollar is still in the bank. So in the bank, there are always some dollars there, right? This number of dollars will be the same as the number of items in the stack. So whenever you do some pop, so you know, when you pop, you cannot pop more than the number of items in the stack. So when you pop, for example, you pop k items. Then you just please take k dollars from the bank, right? I'm very confident that at that time, if you are able to pop k dollars, you must be able to take k dollars from the bank. So in your bank, there will never be deficit, right? Okay, so that's the rationale. So what's the overall cost? The overall cost is just these amortized cost sum. If I associate every push with $2, then you see altogether, I will only deposit at most $2n, right? I will never deposit more than $2n, not possible. Okay, and this $2n are enough, are sufficient to cover all the future operations, right? Okay, so this is about the stack example. Now, I'm not going to do the survey now. After I finish the binary counter, I probably will do the survey. Okay, so for the binary counter, it's the same story, actually. Why? Okay, so now, suppose $1 will represent a unit cost. Okay, $1 represents unit cost. And then you can see that whenever a bit is set or flipped, set to 0, we use $1 to pay the actual cost. And store another one on the bit as a credit. Oh, set should be set to 1. Okay, not sorry, it should be set to 1. Okay, and a bit is reset. We pay that $1 to it. So basically, you see at the beginning, you have all zeros, right? 0, 0, 0, 0. Say okay. The first moment I change this bit to 1. Yeah. I say okay. Then I say okay. I give you $2. All right, $2. $1 to pay the current flip. Another dollar I put it there. Later on, in case you need to come back from 1 to 0, please accept that $1. All right. I will not that flip. I will no longer pay. All right. I only pay $2 when you change from 0 to 1. Okay. So now you see, even if at some moment, you may have many, many ones, right? You say, okay, in that operation, if you increase, I will change to 1000. I flip a lot of points, a lot of bits. Then I say, no worry. Every bit, which is currently 1, has $1 in it. So when you flip it back to 0, please take away that $1. That's it. Okay, so taking away $1 just means cost 1. Okay, means flip of bit. And therefore, you see, whenever you set one bit, you put what? You put $2, right? You put $2 in. And then you know, whenever you increase the value by 1, you at most set one bit from 0 to 1, which is the lowest 0 bit, right? So you only set one bit to 1. So in every operation, I only pay $2, right? Okay, so altogether, I only pay $2n. But these $2n will be sufficient to cover all your future expenses, right? Yeah, the total credit is 2n, not n. So in the worst case, it will be 2n because every time you set a number to 0 to 1, I will pay $2. Okay. Now, of course, you are right. So Jiankun, you are right. In our example, actually, the total credit is n. Okay. I believe it is n because not every operation will. Let me see. No. So I take back what I just said. The total credit is indeed 2n because every time you will set at least one bit or exactly one bit, no matter what you do, right? So for example, you have a 0000. You increase by 1, it becomes 1. You set one bit to from 0 to 1, right? So if you are, for example, if you are this number, right? And then I will set this one to 1 when you increase. So every increase function, right, increment function will set one bit to 1, and I'll pay $2. So it should be the total credit I paid is $2n, and that 2n will be sufficient to pay for all your future expenses. Okay? Yeah, so Xing'an, you're right. For the accounting method, it computes the upper bound of n sequences. You're right. And ignore the specific form of sequence. So basically, when I deposit $2 to the bit which is changed from 0 to 1, I don't care. I don't care in the future at which moment this one will change from 1 back to 0. I don't care. It may be somewhere later, but I do not exactly care when it will be, right? I just pay $1 for future expense, right? Just for future expense. So every step, right? You store $1 in the credit. Oh, sorry. Yeah. So then in this case, Jiankun, you're right. The total possible credit is n, but the total money I paid is 2n, right? I in total paid $2n, but as a credit, it will be only n. Okay. Yeah. So sorry for the confusion I caused just now. Yeah. So basically, you see that. Wow, that's very perfect, right? So at the time when certain operation is taken, you deposit a bit more money in it, right? So it will be sufficient to cover all the future expenses about this specific bit or specific object. And then, well, the amortized cost, they are just covered automatically, right? Okay, so with these two examples, I would like to see whether you have a better feeling about amortized analysis. Okay, great. So it seems that the accounting method is more attractive. Now, although, well, I still see very few students, but, well, it's better than before. So let me just close the poll. Okay. So, last one. The last method is called potential method. All right. So potential method is very similar as accounting method. So which means I prepay something, which will be used later. All right, but it's different from accounting method in the way that the prepaid do not work as credit, but as potential energy or potential. And then this potential is actually associated with the data structure as a whole, rather than with specific objects in the data structure. So you see, in accounting, when we prepay some money, right? So that amount of money is linked to a certain object, right? But potential says, okay, please do not link to a certain object. It's just linked to the overall data structure. Okay, try to see whether that can be explained. Okay, now potential method, it seems a bit more, well, challenging. Okay, it seems that you have quite some symbols, right? Well, remember in the game theory topic, we talk about potential too, right? We say, how about if when you certain agents try to improve its own benefit, then certain potential will increase, right? Always increase or always decrease as long as it's in one direction. That would be good, right? Okay, so let's just briefly talk about this potential method. Now, suppose we have initial data structure D0, and then we have n operations. And then these n operations will bring the data structure to T1, D2, and in the end, Dn. Okay, and the cost will be C1, C2 until Cn. Now, what is potential function? The potential function so for all the phi, so this phi potential function, okay, so this is called the potential of di. So basically, you need to design this phi, okay, so this is not automatically given to you. You need to design this potential function. And then the amortized cost, Ci prime, of the i's operation is what? Is Ci plus potential of di minus potential of di minus 1. Okay, so basically, this Ci is actual cost, right? This Ci is actual cost. And sometimes this actual cost is very big. And that's not good. So I want to balance it by adding the potential of the new data structure and subtracting the potential of the old data structure. And by doing this, you see, well, the summation of the amortized cost will be the same as summation of original cost plus phi dn minus phi d0, right? Okay, so basically all these terms will be somehow cancelled, right? And then only the first term and the last term left. Okay, well, so if we can show phi dn is at least phi d0, which means the potential of the target data structure or the finishing data structure has a larger potential than the starting data structure. Then we go back to this, you see that the amortized cost is equal to this. Now, because this is what? This is larger than 0. So the actual cost will be bounded by the amortized cost, right? So because we want to bound the actual cost. Okay. Now, now because we do not know how many operations will ever be done, so we need to make sure phi di is at least phi d0 for any I. Okay, no matter which I, it is correct. Okay, and then also as a starting point, it is very convenient to define phi d0 to be 0. Okay. Now we see if this difference is larger than 0, then the amortized cost is an overcharge, which means it seems that I give him too much money, right? I give it too much money in that round. Okay. So this is the same as the accounting method, right? So at some round, right, I'm giving a bit more money to this element so that in the future you can use it. So now it is saying that in some round, if the potential difference is larger than 0, then that means actually this Ci prime, I'm being too pessimistic, right? So actually it's not that big cost, but I give him so much, well, a few more dollars, right? I'll give him a few more dollars. And then if this is the other direction, then we say it's an undercharge. Okay, when it is undercharge, we will discharge the potential to pay the actual cost. Okay, so again, let's look at two examples we have. For the stack operation, you see the phi I, right? Phi d0 is equal to 0, and phi di larger than or equal to 0. So how are we going to do it? Well, so basically, what we do is, for push, we change the potential so that it is 1. Okay? So if it's a push, the overall data structure compared to the earlier one, I give him $1 more. Okay, increases. So basically it's overcharge, right? It's overcharge. But now we do not link it to a specific object. We link it to the overall data structure. So I give him $1 more. It's just like I overall give the data structure $1 more. All right. So the amortized cost is CI plus this difference of potential, which is 1 plus 1, right? Because this is 1 for push. This is also 1, and then becomes 2. So basically, you see, the amortized cost for push is 2. And then for pop, the potential change, so phi, we define it to be number of objects in the stack. Okay, this is phi. Phi is number of objects in the stack. So when it's pop, you see you have one less object, right? So that's why it's s minus 1 minus s, which is minus 1. So potential is minus 1. Amortized cost is the actual cost plus potential. Actual cost is what? Actual cost is 1, right? Because you do 1 pop. And then the potential decrease is minus, the potential change is minus 1. So it becomes 1 minus 1, it's 0, right? Okay, good. So that means pop has a amortized cost 0. And then multi-pop similar, because your potential change is minus k, right? Minus k. And then amortized cost is your actual pops plus the difference of potential, which is k plus minus k, which is 0. Okay, so basically, it just links the extra money to the whole data structure instead of the individual object. But the rationale is the same, right? The amortized cost for push is 2, which means every push I give him $2. For pop and multi-pop, we can see, actually, the amortized cost is 0. I don't need to pay anything because it's already compensated by the change of potential, right? Okay, so that tells you the amortized cost of each operation is O1, and then the total amortized cost for n operations over n, right? So it's just very similar as the accounting method, just attributing the credits or money to the whole data structure instead of individual elements. So remember, in this example, potential is the number of elements in the stack, okay? The number of objects in the stack. Okay, so again, binary counter. So I believe that binary counter, it will also be easy to understand, right? So how do we define potential? Easy. We define potential to be BI, which means the number of ones in the data structure, in the string, right? 1, 0, 1, 0, 1, 1, 1, okay? So for this string, the potential is 5, okay? So again, we can compute, right? We can compute the, the different amortized costs for each operation, right? Okay, so suppose, right, the ICE operation resets TI bits, which means change TI ones to zeros, right? And the actual cost of that round is very big, TI plus 1, right? Okay, now if you have a 0 ones, right? If you have 0 ones, then the ICE operation will reset all the k bits, okay? And then so basically you have some way to compute these different values, right? The different values. So basically, in this example, right? In this example, the amortized cost for each individual operation is always 2. Okay. Now these are there are a few details here, but I guess I don't need to spend time to explain it here because it's very self-evident. All right. So basically, after this computation, you are able to conclude the amortized cost for each operation will be 2 exactly, and then that means what? That means okay, in every step I just pay $2. All right. That will be balanced in every step, right? So every step I pay $2, and that will be balanced in the long run. Okay. So this is a binary counter. Now I guess so due to a time limit, I'm not going to explain the details here. This one I will leave it for your own understanding. I guess it's it's totally feasible. Okay, so I guess we'll take 5 minutes break and then we come back to the new chapter. Okay. Yeah, so just want to recap the potential method, right? So the potential method is just a similar counterpart of accounting method, right? Accounting method, when you pay money, you store that money in a certain object. But in potential method, you also pay money, but you do not store the money in certain object. You store the money in the overall data structure. Okay, so that's the only difference here. Okay, now actually I should not take a 5 minutes break too early because we have one last thing which I didn't mention yet. Okay, which is called smooth analysis. Actually, I only have one slide for smooth analysis, but this one is pretty interesting too. I'm not going to talk about details, but try to give you some flavor of the smooth analysis. So, what is smooth analysis? Let me talk about the thing from simplex method. Now remember that earlier, oh, sorry. It seems that it asked me to take a break, actually. The voice is unstable again. Yeah, then 5 minutes break. And then we come back to this and begin a new topic. Let me try to fix it. Yeah, 5 minutes break. So I clicked automatic adjusting mic. Now, is it better or worse? Oh, good. It seems that the automatic thing. Okay, good. All right, then, yeah, I'll come back after 4 minutes. Okay, I will start a bit earlier, half a minute earlier. Yeah, so since this is better, I will use automatic mic adjustment. Now, we start from the so-called simplex algorithm. Remember that earlier we have explained the linear program, right? We try to maximize, say, a1 x1 plus b1 x2, etc., etc., and then with a constraint such that maybe k1 x1 plus k2 x2 larger than or equal to 6, etc., etc. So you have a bunch of linear constraints, and you try to maximize a linear objective. Okay, so this is the so-called linear program. And then at that time we say linear program can be solved in polynomial time, right? Using some kind of sophisticated method. However, in the old days, people simply use simplex method to compute the solution for linear program. So what is simplex method? Simplex method says, okay, you have so basically these constraints gives you some feasible range. For example, this feasible range is a polytop in a high dimension. Okay, I don't know what it looks like, but anyway, it's a polytop, and then it has many vertices, right? So simplex says, okay, I'm doing the following. I start from a random vertex, and then I try to see which direction I move will improve the objective. Okay, so I start from one vertex, and then this vertex has some neighboring vertices, and then say this vertex has 5 neighboring vertices, and then I check among the 5 neighbors which one gives a better objective than my solution. Okay, if it gives me better solution, I move towards that corner, towards that vertex. Okay, so just keep doing it. Whenever you are at the vertex, I try to see neighbors. Which neighbor can improve in solution, right? Compared to me, I move to that neighbor. So you move from vertex to vertex, and eventually you will arrive at some vertex which gives you the best solution. So basically, no matter which direction you move, no improvement. Then I say, okay, that's my solution. That's the optimal solution. Now, of course, I'm not going to talk about the proof of this method, just showing the process. And then this method actually, in the worst case, will take exponential time. It's not fast. But in practice, people observe, well, it usually ends very quickly. So then researchers start to think, what's the reason behind? This is an exponential time algorithm, but in practice, it runs very quickly. Any magic behind it? So this magic is exactly the smooth analysis, where the smooth analysis comes from. So what is smooth analysis? So smooth analysis says following. Now, you have many possible problem instances in the whole space, many. And there may be one instance which takes a lot of time, right? Exponential time. So indeed, there are problem instances which will take exponential time to compute the optimal solution using simplex. That's for sure, all right? Okay, so but the good news is what? The good news is if you look at this instance's neighbors, which means I perturb or change the parameters slightly, okay? For example, I change k1 by 0.00001, I change k2 also by the same amount, etc., etc. I change the parameters very mildly so that the new instance is within the range of the old instance, a very small neighborhood of the old instance. Then the running time suddenly drops a lot. Okay? So basically, you see, you have a bad instance somewhere, but these bad instances are somewhat isolated. So there will not be a lot of bad instances squeezed together, all right? Whenever you see a bad instance, in the neighborhood, almost everyone is good, okay? So smooth analysis says, okay, now I would consider the running time of a certain thing to be averaged among its neighbors, all right? So I have one person which is very bad, okay, very bad, but his neighbors are all very good. So if I take an average over the whole neighborhood, they will be good, right? The running time will be good. So that explains the phenomena. So in reality, the problem instance, usually they have very rare chance going into those very, very tiny bad point, okay? Instead, it may fall under, well, within the neighborhood. And if it's within the neighborhood, the time is pretty good, okay? So that's the rationale behind smooth analysis. It is taking an average over the running time of all its small neighborhood. So they show that for simplex method, if you do this, then it is polynomial time solvable, okay? Well, so as I said, this smooth analysis is just a very high-level sketch. So I hope you get the point, okay, or the rationale behind the smooth analysis. Yeah, so because I do not quite know Dirac delta function, but I believe since you raised this, both of you, then it's most likely the case. Okay, yeah, so any question? We basically finished everything in the previous sessions. And then if no further questions, I will go on to the next one, cooperative game theory, which is also very, very interesting. Let me open the slide. So actually, this is the slide which I basically borrowed from Edith Elkind in Oxford University when she gave her course on cooperative game theory. So her slides is very nicely made. So basically, I only changed a very few things of her slide. So yeah, let's start. Now, cooperative game theory, most of the materials here come from her book, The Computational Aspects of Cooperative Game Theory. If you're interested, you may go to take a look. It's also available online. Okay. Now, the outline of this chapter, basically we use the remaining hour and also next week's 3 hours to cover this topic. So basically we'll introduce the cooperative game theory and also examples of games. And for cooperative game theory, we will talk about the so-called stability. What kind of solutions are stable? So this is somehow like Nash equilibrium, but a bit different. Okay. Now here we'll talk about core and least core. And we also will talk about the fairness in cooperative games, basically Shapley value. Now you know that in the previous lecture, we already give one example about how to compute Shapley value, right? About all the permutations of arriving order. Okay, so this is will be covered in more detail here. And then we'll also talk about games with non-transferable utility or hedonic games and talk about the Gale-Shapley algorithm. Okay. So let's start. Now, remember that when we talk about Nash equilibrium, basically, it's in a non-cooperative setting. You know, remember that in the Nash equilibrium definition, you say each agent or each player does not have any incentive to deviate from its current strategy, right? So it always talks about a single player. Single player will not deviate. So basically, they are not cooperating, right? Okay, so in this no cooperative games, each agent will choose her own action, and the payoffs or utilities also will be computed based on individual agents, right? But for cooperative games, the utilities usually is transferable, which means agents will form groups, and this group will get something in total, and then you can divide this total benefit to the group members so that they will not have incentive to deviate. Okay. Now, remember that here the actions are taken by groups, not agents. Okay, and then the payoffs or utilities, they will be computed based on groups, and eventually will be divided among the agents. Okay. Now here, first example is called happy farmers. Let's see. Now there are n farmers, and they can cooperate to grow fruit. All right. So there are some people like this, right? And then each group of farmers, they can grow either apples or oranges. Now, for example, these two will grow apples, and the other two will grow oranges. And then here is the rule. All right. If you have a group of size k, they can grow k squared tons of apples and or 3k tons of oranges. Okay, so basically, well, apples seems more efficient for a larger size group, right? For example, if you have 10 people, then you can grow 100 tons of apples, right? And then if you have 10 people, you can only grow 30 tons of oranges. Okay, and then these fruit will be sold at the market, and then the price. Okay, so here is the price. Sorry, this is the only place I did. So basically, you will sell for $200 per ton for apples and $300 per ton for oranges. And then, so what are the actions? So here we need to make some assumption. For example, we need to assume that actions of one group will not affect the utility of other groups. Now, before I show you the next thing, so do you agree about this? Now, this is the assumption, remember? This is an assumption. So, yeah, so while you are thinking, so these assumptions, please think about whether it is reasonable or not, right? Action taken by some group will not affect the action taken by other group. And meanwhile, I will actually answer Xinran's question about the smooth analysis. Sorry, I overlooked this question earlier. So basically, it's not about restricting search domain to a very small neighborhood. It's about when you compute the running time of a certain point, we do not compute the running time of that exact certain point. We compute the average running time of a neighborhood around this point to be the expected or anticipated running time of that point. Okay, because it's not restricting the searching domain. Okay, so well, it's only a short answer. If you still have questions, you may ask me after the session is over. Okay, so Wing-Chun said that they won't cooperate if they can affect each other. Well, so actually here, if they will affect each other, then the game will be super complicated, I think. Okay, so basically, in cooperative game theory, this is an assumption which must be made. All right. Now, but of course, you say if they can affect each other, then probably I can also do something. Well, that's possible, but not in the general sense. All right. Yeah. And then Xinran said, yes, in real situations, the action may affect. That's right. Okay. So because in reality, the prices will depend on demand and need, demand and the supply, right? So basically, if you have more oranges, and then orange price will be lower, right? But here you see, we're assuming they have fixed price. That's why their actions do not affect others' gain, right? Okay, and then based on this assumption, you will see that each group's payoff is totally defined or determined by its action. So I guess the other two questions in the chat, they express your concern, okay, about the assumption. But anyway, we have to use the assumption in order to get some results, right? Okay, so now with this assumption, then actually we can assume a follow-up thing. We can assume the group will choose an action with the maximum utility to the whole group, okay? So what does it mean? For example, a group of size 3 farmers, they can earn $1,800 when growing apples, right? Okay, so remember the function, k squared tons, right? And apple price is 200. So k is 3, k squared is 9. 9 times 200 is 1,800. But a group of 3 can also earn 2,700 growing oranges, right? Because oranges 3K, right? It sells what? It sells at 300. So it's $2,700 for oranges. then definitely they will not choose this one, right? They will not choose apple. Definitely they will choose orange. So basically that will make our problem simpler, right? So we can abstract away actions, or no longer have actions. We just have what? Utility. When you give me a group, I just know how much utility this group can get. Okay? Okay, so Jianchong asked, are these groups already formed? Well, actually, this is about arbitrary group. So it's any possible group. For example, if you have n persons, you have 2 to the n possible groups. Okay? We will analyze, or we will study the behavior of all these groups. They are not fixed. They are not, they are kind of a exhaustive search. Okay? So every group has utility we need to consider, because in the end, our solution should be robust towards any deviation, right? So you should analyze the behavior for all the groups. Okay, so I hope I answered your question. Okay, good. So now, you see, for this setting, right, you don't need this, right? You just need that group of size 1 can earn $900, and then group of size 2 can earn $1,800, and groups of size 3 can earn $2,700, and so on and so on, right? Okay. Now, another example. There are no interaction among groups, okay? No interaction. Very good question, Xiao. Now, actually, we didn't finish all the concepts yet. So after we explain all the things about the cooperative game theory, then probably it will be clearer, all right, about interaction. So basically, the focus of study is only on individual group, okay, individual groups. So another example is buying ice cream, right? So suppose we have n children, and each child has some amount of money, and each child has BI dollars. And then there are 3 types of ice creams. The first type, 500 grams, and it costs $7, right? And then type 2, 750 grams, it costs $9. Type 3, 1 kilograms, cost $11. Okay, so children will have utility for ice cream. They do not care about the money. Okay, so basically, how much money they will be left with, they don't care. They just want to use all their money to do something, right? To get as many or as much ice cream as possible. Okay, and then the payoff or utility for each group is the maximum quantity of ice cream the members of the group can buy by putting their money together. Okay, so let's see. The final thing, within the group, the ice cream can be shared in an arbitrary way, as long as this sharing will be beneficial for preventing those children to deviate. Okay, so let's see. Now, how to play such a game. Now, that's a very important thing, right? So in a non-cooperative game, we are very clear how it is played. You fix an agent, and then this agent says, okay, using another strategy, I can get better utility. Then he just used another strategy, right? So this is how non-cooperative game is played. And in the cooperative game, although they somehow work together, right? But they are still selfish. They will still, well, deviate. How to do that? Well, so you have to guarantee something. Now, basically, you will partition you will partition it into some coalitions and some utility distribution or payoff distribution. You should guarantee that no player or group of players has any incentive to deviate. Okay? Now, we'll show examples very soon about this. And then we also somehow want to make sure that the outcome is fair, which means the money or payoff of each agent is proportional to his contribution. All right? So he contributes more, he should get more. And this is about the Shapley value, right? Okay? And then let's try to formalize these things into mathematical Now, we have the following cooperative game, which is a pair, N and V. So what is N? N is all those participating players, all right? 1, 2, 3, 4 until N. And then V is the characteristic function. So what is this characteristic function? So this characteristic function means if I give you a set C of players, VC is the amount that members of C can earn by working together. So this is exactly the profit you can earn by growing oranges, growing apples, right? So remember, if you have a size 3, you have a size 3 of people, then you will get $2,700, right? Okay, so VC just means how much money this group of size C, this group of C, right, can earn, right? So this group of C, well, this value may not only depend on the size of group, may also depend on members of the group, right? Okay, so this is about the value function, right, or characteristic function. And we usually assume that the V is normalized, which means if you have nobody in, V is 0. Oh, this is very natural, right? And then also non-negative, which means you have a group of people, then the V will always be larger than or equal to 0. You will never get negative value. That's very unlikely, right? Okay, and also will be monotone. You have more people joining in, you should somehow get more value, right? Or produce more value. Okay. And then a coalition, which means some people working together, right? So a coalition is any subset of the group of players, and then the N itself is called the grand coalition. So this one you probably need to memorize, okay? So grand coalition means everyone in, okay? You put everyone in, this is called grand coalition. And usually in many games, we hope the grand coalition can already achieve the goal that nobody is trying to deviate, okay? So this is our ideal goal, right? We hope that grand coalition is good enough, okay? So now let's see the ice cream game's characteristic function. Now suppose there are the three children, right? C has $6, the M has $4, and this P has $3. And then the ice cream, remember, it's these three sizes, right? Okay. Now, how to compute? Well, you see, V empty set or V of any single child will be 0 because their money, individual money, is not enough to buy any ice cream, right? You see, 6, 4, 3, and then ice cream is 7, 9, 11. So each one of them individually cannot buy anything. Next, how about C and M together? I put these two persons together, they have $10. What can they buy? They can buy this, right? Okay, so their value will be $750. And you put C and P together, maybe $9. You can also get $750, right? It's also sufficient. And then M and P together, they have $7. Now $7, you can only buy the smallest one, 500, right? Okay, so now you have the V of the 3 people. How about V of 2 people, right? 2 children. How about 3? Oh, 3, of course. You have $13, then you can buy what? You can buy the largest one, right? 1,000. Okay? All right, so I would like to stop for a while to see whether you can follow the examples. So my question is, can you follow the example about this ice cream game? Okay. So, well, I stopped the polling. Now, actually, some of you still didn't get it, but, well, I just want to say that, well, yeah, later on we'll come back to it again. So basically, here we are computing for different people. The combination of different people, they have a total amount of money, and then this total amount of money can be used by a largest possible set of ice creams. Okay, so now I ask you one question. If somebody's added up money is $18, then what should be the value of this group? Okay, very good. It should be 1500, right? Okay, yeah. So just to make sure that well, it's not always it's not always the case that you can only buy one ice cream, right? Sometimes you can buy two, right? If you have $18, of course you can buy $7 and $11, or two $9, right? They have the same value. Okay. Well, so next there's another game. Well, so it's another definition. Okay, further definition. Now, this type of games, we call it transferable utility games, which means if a group work together and get something, this something can be arbitrarily distributed to the members. All right, so that's why we call it transferable utility games. And then in transferable utility games, the outcome need to be specified as a pair. Okay, so what's the pair? Okay, so the pair has the following meaning. So CS, okay, computer science, right? Though it's also coalition structure. So basically, you divide the whole graph into groups of people. Okay, this red group, this green group, right? And then you need to make sure the group altogether will be the whole set. And then each of them has no overlap. Okay, so basically it's just a partition, right? It's a partition. And then you need to specify the payoff vector, which is x1, x2, x3 until xn. So telling people how much money or how much value you should give to each individual player, right? Okay, so you need to make sure everyone gets a non-negative value, right? That's for sure. And also, you need to make sure that the money you give to each agent, they add up to VC for each C in the coalition structure. Okay, so basically, for example, people, the 1, 2, 3, three people, they work together and get $100. And then you need to distribute this $100 exactly to these three people. You cannot put any money to that other group, okay? That's not allowed, all right? You need to make sure that the money you earn by this group has to be redistributed within the group members of this group, okay? So I bet this is a quite natural requirement, right? Okay. So, example. In this figure, we have two groups, right? V1, 2, 3 equals N, which means they can earn $9. And then V45 is equal to 4. They can earn $4. And then this is a so-called outcome. Why? Because you see 3, 3, 3, they add up to 9, right? The first three person, they get $9. The last two, they get $4. That's good, right? Okay. And this one is not an outcome. Why? Because you see the red players, they only get $7, but they can earn 9, right? So that means $2 are given to the green one, right? That's not good, all right? So although it's transferable utility game, but you cannot transfer the money earned by one group to group members of other groups. Okay, so I hope this is clear. And then an outcome is called an imputation if it satisfies individual rationality. Okay, so this one is also a kind of a special word. I bet that before this lecture you didn't see it. Many of you didn't see it, I see. So this one is a very natural requirement. So we need to make sure that xi is larger than or equal to vi. So what does it mean? Why do we have such a requirement? The money I can get is larger than vi. What does it mean? Oh, very good. So Jianchong, you get the bonus. So basically, in your decision, right? In your decisional partition, it should be better than everybody work by himself, right? So you should not have any one person who gets money less than the money he can earn by himself, right? Okay, so that's the very, very natural requirement. And the reason that it is called individual rationality is that, well, you want to make sure that everyone is willing to join the game. Otherwise, this person will not join. You say, okay, why not just work alone, right? Okay, so this is individual rationality. Now, we will use XC to denote summation of the money the agents in set C get. Okay, so XC, so it's for convenience. All right, so now again, we come to the ice cream game. You see that, well, if the coalition structure is this, CMP, right? And then the X will be 0 because nobody can afford any ice cream by him or herself, right? That's okay, right? So that's a possible one, right? Possible reasonable one. And then you can also have this, CS is equal to CMP, right? So C by himself, and then M and P together. And now you say, I will divide the money, divide the ice cream in this way. I give M 100 grams, I give P 400 grams. Well, up to now, it seems still fine, right? Because altogether, they too can get this ice cream, right? 500. So I divide the 500. That's okay. And then if you, about this grand coalition, right? Everybody together, then is it okay? Well, then you see, you buy 100 grams, right? And then you give each of them some grams, right? So I'm doing a very even division, right? Each of them get about 333. Okay. And then we also can do the other one. It's also grand coalition, and now the ice creams I give to each person is that the M get 800 grams, and then P get 200, and C gets nothing. Okay, so this is also one feasible the outcomes, right? Okay. Now, yeah, so I guess up to now it should be okay, right? So these examples are just showing you all these things, all these allocation or division, they're reasonable, right? Although you may say, this one, right? Give him $0 seems very unfair. He has the largest amount of money, right? $6, you give him 0. Well, according to what we just defined, you cannot criticize this solution too much, right? So that means our tool is not sufficient yet, okay? We need more tools to avoid this kind of division, right? Okay? Okay, so now let's talk about one interesting subclass of games called super additive games. So what are super additive games? Well, and now here there are some keywords, right? There are sub-additive, super additive, and later on you will see super modular, and we also have sub-modular, etc., etc. So we'll know these differences very soon. But for now, we just focus on the super additive. What does it mean by super additive? Actually, it's very easy. It just says that if you have two disjoint coalitions or disjoint sets, C and D, okay, they do not have overlap. And then the value of the union of these two groups will be larger than or equal to VC plus VD. Okay, so basically it just means bigger group always better, right? Well, superset always better. Okay, so you have a superset of groups. So you have group 1, group 2. Then it says, okay, if you two groups work together, it will be even good, even better, right? So one example, suppose VC, the value of a group, is the size of group. Then what can you say? Easy, right? So then V of C union D is just the size of C plus size of D because they two have no overlap, right? They have no overlap. And then it's just the VC plus VD, right? So basically it's equal sign. Equal sign is a special case, right? So it's also super additive. Okay, so Xiao is asking a very good question. what will the payoff to one agent decrease in a larger group? Well, possible, right? But you can make sure it does not decrease, right? I believe there is always a solution. So because you see, for smaller group, you have a certain way of dividing the money, right? And then for this VD, you also have a certain way to divide the money. And then because if you work together, you have more money. So I can keep your original division, original allocation of money. So everybody will be happy. And then I give the extra to evenly to all the members. Then all of them will be happy, right? So basically, although it's possible, but it most likely will not happen because we can just follow our distribution of money in individual groups and then give the extra money evenly to all the group members, right? But you are raising a very good question. Okay, so this is the, so Wing Chong asked, what if adding more members does not add more gain? Okay, even if adding more members does not add more gain, it's still fine, right? So, so it's larger than or equal to, right? So it's fine that everybody just gets the same as before. Now here, it's about the, because this one, we are trying to show the grand coalition is the best, okay? Everybody work together is the best. Nobody will deviate, right? Okay, so that just means, so when will somebody deviate? Only when they can get strictly better or more money, right? But if it is super additive, then no subgroup can go out and get extremely more, right? So we are just trying to prevent such kind of deviation. It's just like in the Nash equilibrium analysis, we say sometimes people may deviate. They may change strategy to get more. But if they change strategy, they can get equal. Will they change? So the answer is yeah, no, they will not change. Okay, they will only change if they get strictly more. All right, so same as here. Even if it's just same, equal, it's still sufficient. Okay, yeah, so then I'll answer the questions, 2 questions in the chat. So Ziao asked, then the Nash equilibrium will always be the situation where everyone is the same group. Yeah, you're right. And actually here we do not have the so-called Nash equilibrium concept. Okay, we do not have the Nash equilibrium, but it's a stable state, right? No group will ever try to deviate or try to separate out to work on their own, right? So this is the solution concept here. And then Wing Chong said, asked, so even someone would get less if adding more members, it is still better than not joining the Grand Coalition. This point, I guess it's not quite the way. If you add more members, we will try to maintain the property that everyone gets at least as much as before. All right, they will not get less. If they get less, probably some group will deviate. Okay, so okay, good. Now let's continue. Now one another example is about VC equals C squared. Okay, psi C squared. Now this value becomes what? Becomes C plus D squared. It becomes C squared D squared and plus 2 times C times D, right? So definitely it is larger than or equal to the 2 squares together, right? And then this one, right? This is easy. This respectively are VC and the VD. Okay, so square is also super additive, right? But well, you can guess that. Well, you already know that the square is super additive, right? It's a square. Okay. Now ice cream game. Ice cream game, is it super additive? Okay. Yes. Yeah. So basically, you have more money. Now earlier, right? So earlier you can buy this certain amount of ice cream, and using this money alone, you can buy a certain amount of money, a certain amount of ice cream. If you pool these money together, then, well, of course, you can still use the original plan to buy ice cream separately, right? But because now you have a bigger amount of money, you have more flexibility to choose, right? So Well, possibly you can buy more money. At least not. It will be as at least as good as the before, but maybe better, right? Because you have more flexibility of making the composition, right? Okay. So so this is about the ice cream game, right? So it's also super additive. Now in super additive games, two coalitions, they can always merge without losing money. That's very good. So that's why we can assume players will always form the grand coalition. Okay, so yeah, I guess this is the major purpose that we introduce this super additive games, right? Because in this case, grand coalition, which means everybody work together, will be very good, right? But you need to figure out some way to distribute money, right? Otherwise, some people will be unhappy, right? Okay. Now here is another example. It's called induced subgraph games, or we could talk about we call it friends and enemies game. Now, what is this? So you know graph, right? So in our algorithm session, we already know graph. And then this game says, okay, I have a graph, and if you give me this graph, every player, they are vertices of the graph. Okay, every player is a vertex of the graph. And then the value of a coalition is total weight of internal edges, which means, well, for example, if it's T, right? If it's T, then you have 3 vertices, and it only cover 2 internal edges, which is X and Y, right? Okay, well, so the weight is just the weight of the X, just X, the weight of X plus weight of Y, right? Okay, so this is the value of T. And for value of S, then it's just 4 edges, right? S has 4 nodes, and 4 edges, you just do X plus Y plus Z plus T. Okay? Now, usually it can be used to model the social networks, right? So you can say, oh, with edges, there are some kind of friends, right? And then, well, you have a more friend relationship, then you will get more, right? Now, the question is, are induced subgraph games super additive? Okay, I see some. Okay, good. Now I see many answers, right? So I'll give bonus to some of you. So actually, right? Let me just write down the bonus people. Okay, so so 建聪文雪珍, you will get the bonus. This is also a half bonus. So basically, if your weight is non-negative, then it is super additive. Yeah, because if you have, if you have negative edges, right? And then if you combine these two sets together, they will have some new edges introduced, right? So if these new edges have negative weight, then that means combining 2 groups together will be bad, right? Okay, and that's also where the enemies come from, because the edges not only mean friendship, right? It can be positive weight means friends, negative weight means enemies, right? Okay, so this game, right? Only if the edges are non-negative weight, have non-negative weight, then it is super additive, right? Okay, well, so nice. Now next one. So let me know if you have anything unclear about the games we introduced so far. All right. Okay. So we have some convention in super additive games. So basically, we would identify outcomes with payoff vectors for the grand coalition, right? Because yeah, so we said that for the super additive game, although it's very good, but you still need to find a way to distribute money so that nobody will complain, right? So an outcome of the super additive game will be a vector x, right? So the payment, right? The payoff vector. You need to add up to the value of the whole set of players, right? And for any non-super additive game, G, it can be transformed to a super additive game by doing the following setting. Okay, wow, this is a bit interesting, right? So how to do that? So basically, we would define another function, v, which is the maximum of any possible partition of the members in C, and do a summation. Okay, then it becomes super additive. So what does it mean? Now, you see, earlier when we talk about VC, right? VC, so this one, right? VC. So if it's VC, now, well, actually, this value, this whole value, it may not be quite, well, it may violate the super additive, just like you have negative weights, right? When you have negative weights, then when you combine these two things together, it's no longer super additive. But if you compute this max, so you have two groups, you want to merge them together, it may be worse, but no worry. I take all of them together, I consider all the possible partitions, and then I would add all the value of the partition together and pick the best one. If I say the value of the whole set is the value of the best partition, then it becomes a super additive game. Well, so this one probably needs some time to think about it, but I believe it is not difficult to understand. Okay, so as I said, right? So this PC is all the partitions of the group C. Right? Okay. And then we say GSA is the super additive cover of G. Now, I guess we will just briefly try to briefly understand why it is the case. All right. So can we prove it from the definition? If we define the value of a set to be the maximum total value of the partitions, right? For any partition of the group. Yeah, so Xingran, you're right. This max leads to super additive. So think about it. Yeah, so you are right. We have more combinations. So basically, you see that so if you have a union of S and T, right? Oh, sorry, not U. Okay, S union T. Okay, sorry. So S union T, the V of S union T is no longer Vs plus Vt plus something. So basically, it could go to, well, different. Well, the value is not limited to one possible division, right? So it can be the value of all the possible divisions, right? Okay, but anyway, I guess we will not talk about the solution now, but I would like you to think about it, whether why this is the case. Okay. Well, so actually, yeah. So actually, this one would be now it's only week 6, right? Okay, but I would like to say that probably or not probably, most like well, for sure we'll use this one as one in-class exercise. Okay, why this max thing will guarantee it's a super additive game. Okay, so this is now we have 2 in-class exercise. The first one is already there, right? This will be the first question in the second one. Okay, the second in-class exercise. 1 question in second in-class exercise. Okay. Okay, so next one, I will just briefly mention the game, but the main thing will be talked about in the next lecture. So there's also a game called weighted voting game. So the scenario is something like you have n parties in the parliament, and then party I has WI representatives. So basically you see the larger number of representatives party I has, then the stronger power it has in arguing for something, right? Yes, Ziao, you're right. The question is to prove transform game is super additive. And then in this party game, a coalition of parties can form a government only if its total size is at its Q. So basically it's kind of every party has some number of members, and then you want to select some parties to form a government, but their total count of the representatives should be at least Q. Okay? And then usually Q should be majority, right? It should be summation of Wi over 2, take a floor plus 1. So it should be strict majority, all right? Not only half. Half is not sufficient, right? Okay. And then WC will be equal to summation of WI for all the party I in the group C, right? Okay. Now, this setting can be described by a game where you have the following players, right? 1 to n, and then value of C will be equal to 1 if WC is at least Q, right? Okay. Now, if it's less than Q, VC will be 0. So it's a binary value, right? Either 0 or 1. Either can form a government or not, right? And then the notation will be something like this. G equal to Q, W1, W2 until Wn, and then this Q is called quota. Okay? Yeah, so I guess today we just stop here, and then next lecture, in next week, we'll continue of this along this line about the cooperative game theory. Okay, so now question time. If you have question about any earlier part we covered today, feel free to ask me. And then just to want to emphasize, the midterm will be week 10. Okay, didn't change. Week 10 lecture time, and then the midterm will be 2 hours only, and we will have 1 hour lecture followed by 2 hours midterm. Okay, so the 1 hour lecture will be before the midterm. Okay. Yeah, it's confirmed to be on March the 24th. You're right. Yeah, let me just recall the assignment release. So the assignment release time supposedly should be week 4, 7, 9. And then because we shifted 1 week, it becomes 5, 8, and 11, right? So the deadline should not be week 9, I think, in this case, right? It should be week 11. Yeah, anyway, if you are already on the way of solving those OJ questions, just keep doing that. Yeah, the deadline is not very close. Now, Jiankong asked me, will the exercise tutorial and assignment questions be explained to us later on? Yeah, so about this question, what I could say is the following. About tutorial 1, definitely, I will explain the answers to you, with you, okay, in some later time. And assignment questions, I will not explain, but I probably would provide a sample answer, okay? Yeah, so these are about the 2 things. And Ian asked me, now we have 3 in-class questions in total. Wait. So remember, today's in-class question, it belongs to the second half, all right? Not first half. It belongs to second half. Do not include it in your solution in the first half. Use a separate file, and we have more to come in the future. So basically, everything about game theory, it is by itself. So we have 2 parts: algorithm, game theory. Algorithm has its own in-class, and game theory has its own in-class. Okay, you need to separate it. Okay, good. Any other questions? Okay. Yeah, so another 2 questions. Yes, you're right. First in-class exercise consists of 2 questions in class and 4 questions in tutorial. You're right. And Zia asked, not choosing OJ is okay if I finish all proofs. Yes, you're right. So basically, all the 3 assignments, they will be sufficient for the coursework. OJ is only for those who think the proofs or something is too difficult, you would like to choose programming instead, then this is the alternative way. Yeah. Okay, good. Yes. This week, you need to upload tutorial questions and the 2 in-class questions in the first half. You are right. Second half, the due time will be the end of semester or week 13, okay? Because it will span the whole game theory session, so the deadline will be week 13. But my suggestion is just to keep, try to do it when it is released, and then in the end, it will be very easy for you, right? Just to submit the whole. Okay, you're welcome. Yeah, so sorry for the bad the mic quality today. I should have brought a headset, but it's good to figure out the automatic adjust. So I guess after I switch to automatic adjust, everything is okay, right? It's no longer very. Actually, no. Oh, sorry. Too bad. But I hope you still roughly can follow. I agree. I will ask my lab our lab to change a mic for me or change a computer. Yeah, but yeah. Yeah, so I really sorry, really need to apologize for that. Yeah, yeah, it's good to know it's better than before. Well, anyway, it's just a solution out of well, no choice. So so I guess the recording also has similar problem. But anyway, thank you for paying attention in this difficult times. I will definitely remember to bring the the headset. You mean I turn up the volume? Yeah, so. Oh, okay. But on my side, I guess I cannot do much, right? So only headset can solve the problem. I have no way to change my volume. Not so good at the technical stuffs. Okay, yeah. So let me know if you thought of some possible improvements of the situation of this mic problem. Yeah. But anyway, I will remember to bring the headset next time. Okay. Yeah. Then if there are no further questions, we'll see each other again next week. And yeah. Yeah, sure. You can ask a prop in midterm. Yeah, ask about questions on midterm. Please go ahead. Yeah, you can consider assignment to be a midterm to be similar to assignment 1 or in-class questions. And also there may be something which didn't show up yet, because for game theory part, we didn't have any assignment, and also not only one in-class question, right? And actually, I would say that it should be easier than assignment, because anyway, we are requiring you to finish the question in 2 hours only. So it will be easier than assignment. Some of them, at least. Okay. Yeah, thank you. Then see you next week. Thank you.